There's a charming story that Albert Einstein told about when he was a little boy. A family friend gave him a compass as a gift. And he was a small child, but he remembered that that compass just fascinated him. He said that it gave him a sense that there was something hidden around him in the universe, something deeply hidden in the way things worked. In this video, I'm going to show you some simple ideas about magnetic fields, and most of these you can understand simply by knowing vector addition. You don't have to know any of the technical, complicated stuff about magnetism that has to do with how magnetic fields work specifically. It's more like just general stuff about how vectors work, because all vectors work the same, and the magnetic field is a vector. Let me give you a better view of this. Here it is flat on the desk. A compass won't really work very well if you try to tilt it too much, because the bearing will stick. And we have the two ends arbitrarily painted different colors, one red, one white. This is a completely arbitrary thing. If we were to get in radio contact with aliens in another galaxy and had no external points of reference, we would have no possible way to tell them what's our convention, which end to paint red and which end to paint white. We would actually have to get together and have some common point of reference to establish that. This is the direction of a vector, which is the magnetic field vector, and it's the magnetic field of this room, which is actually nothing like the magnetic field of the Earth. This compass is not pointing anywhere near north right now. There are magnetic building materials in this building that are what are basically creating the field that this is responding to. It's actually a pretty weak field. If I want a stronger field, I can take this magnet out. This is a neodymium magnet, so it's quite strong. I've again arbitrarily labeled the two ends with colors, one white, one blue. And really what's going on here is this is one magnet and this is another magnet, and they're going to interact with each other. But for our purposes in understanding what's going on, it's actually kind of nice if you just think of this one as a measuring instrument that measures the field made by this. And this one, because it has a nice bearing and can rotate, it's going to accommodate itself to whatever this one wants. So if I bring this one close, I get effects that are very strong. And I can show you that there is a polarity involved here between the white and the blue. So if I come in from this end, let's take the red as our definition of which way is the magnetic field vector. So that means that the magnetic field pattern outside the white end of this magnet points away from the white end. On the other hand, if I flip it around, this shows us that the magnetic field outside the blue end of this magnet points into the magnet. I can also come in sideways, and that kind of measurement shows that the magnetic field alongside the magnet is parallel to the magnet. So if I want to draw that pattern, then this is the sort of pattern I get. So at every point in space, I get a vector which tells me what direction is the magnetic field at that point, and also how strong is it. The compass is not a very good instrument for measuring the strength of a magnetic field. It only really directly tells you the direction of the magnetic field. That's why it has a little angle scale on it. Only indirectly can you get strength information from it. So I'm not trying to show that on here with these vectors. But in general, the pattern is sort of like a fountain pattern. So it comes out at one end, goes in the other. And it's pretty visually compelling that I kind of want to chain these together, hook them up like a train. So if you do that, you get what are called magnetic field lines that form closed loops, at least in this example. One interesting thing that you might then ask yourself would be, what happens to the lines when they're inside the magnet? Unfortunately, we can't take this big solid object and stick it inside the solid magnet, but you could imagine there are sort of two logical possibilities. You could think that, well, maybe these magnetic field lines start at a certain point and then they come to the end of the road and stop. So then you would say, okay, there's a pole here, a magnetic pole, and then there's some other magnetic pole here. The other thing that you can imagine is maybe they actually just form closed loops that actually come all the way through the magnet itself. and in that case there would be no poles. And so well, we're going to actually do an experiment that gets at this, although clearly we can't get at this issue just with that bar magnet. To show you the vector addition idea, I'm going to take this magnet and put it right there. So at that distance, that magnet's field is much, much stronger than the ambient field in the room, and basically it's single-handedly dictating which way the magnetic field is going to be at that point. Then I'm going to take this other magnet, which as far as I know is identical. It might not be magnetized with exactly the same strength, but probably about the same. And I'm going to bring it in like this. And I think you can see that when I get them to about the same distance from the compass compromises at an angle of 45 degrees. So this is a classic example of vector addition. If I've got one vector like this and another vector like this at 90 degrees to it, and they're equal strength, to do vector addition we need to slide them around so they're tip to tail. So I'll do that. And then the vector sum is going to be this vector that goes from the tail of this one to the tip of that one, and they form a 45, 45, 90 right triangle. Take a look at this monster. This thing weighs a few pounds, I think. Huge horseshoe magnet. And we can investigate its magnetic field pattern in the same way as we did with the bar magnet. So I go here, I can see that the magnetic field is pointing in to there. But if I go over here, the magnetic field is coming out of there. So it's some kind of a pattern that goes like this. And actually it's not that different from a bar magnet that's just been bent in the middle. And again, there's this question we can't get at yet, which is what's happening inside the magnet itself. Now here's another cool toy. This is a magnetic field sensor, this wand I'm holding in my hand. So right now it's measuring the magnetic field at this point in space. That's that little 2 centimeter tip of the sensor. And it's saying that many units, those are units of millitesla. Like Tesla, capital T, like the car, named after the same person, is the SI unit of the magnetic field. And because the magnetic field is a vector, it has different components. So I can say I'm going to measure the component along the x-axis, and it's that. Now I'm going to measure the component at that point in space along the y-axis, and it's that. And then along the z-axis, I'll get that value. The nice thing about this thing is, unlike the compass, it lets you measure the strength of things. So if I start about this far away, let's say, from the horseshoe magnet, I'm getting almost 1 millitesla worth of field. And then if I get closer, as we would expect, the field gets stronger and stronger. And at some point, I'm going to max out the sensor. I want you to see that. Now it's reading 8.22 millitesla, and notice how the numbers are no longer fluctuating as my hand shakes. That's because I've saturated the scale on this sensor, so no matter how close I get, it's still going to read that number. And since we think that the magnetic field pattern of this thing, based on the compass, must be going in one pole and out the other, we would expect that if the magnetic field pattern is some value like here, let's say about 4 millitesla-ish, if I go over here, I should get about -4. So let's try that. And I do get about -4. Of course, it's very, very sensitive to where I hold it. I've got this cubicle cardboard box that I made up for my students for a lab exercise, which I tried to figure out how to have them do at home during the COVID epidemic, but it wasn't one that we were able to adapt for them to do at home. So this is kind of me doing the lab here at school. And so this thing does have a magnetic field. So if I bring the wand over here and point it into the box, I get negative readings. Over here, I'm getting sort of small, mostly positive readings, kind of a big positive reading down over there. So it's just some lumpy asymmetrical thing. That's how I constructed it. And now we can get at this whole question of whether the magnetic field lines start from one place and end at some other place, or whether they always form closed loops. Here's our rough pattern that we drew for the bar magnet. And we just weren't sure whether the field lines started at a pole and ended at an opposite pole, or whether they actually connected through informed closed loops. And so let's just say that you have some random magnetic field like this, and let's imagine that you pick some cubical volume of space. Let's say that right there. Then in general, you would have a different number of field lines coming out of the box than going in. In fact, the way I've drawn this, there are no lines going into the box at all. So I'd have 2 out and no in. And if I subtract, I would get 2 minus 0. So I would say that there's a net magnetic flux of 2 units coming out of the box. On the other hand, if you believe that these magnetic field lines always join up and form closed loops, like that, then it would always balance out. Here I would have plus 2 units of magnetic field lines coming out. It's called magnetic flux. But I would also have 2 coming in through the bottom of the box. And if you take the hypothesis that these magnetic field lines never begin or end at a certain point in space, then it's an ironclad prediction that no matter what kind of box you pick, no matter how lumpy and asymmetrical the magnetic fields are, they could be caused by something inside the box or outside the box. It shouldn't matter. If you measure how many field lines come out and how many field lines come in, it should always balance out to 0 for the total. So we can actually test that hypothesis using that box, which actually does have a magnet stuck inside it. Here's the thing. I need to measure the field all over the exterior of this box, right? I can do the top, I can do the front, and so on. How am I going to do the bottom? There's no way to get underneath there to do the bottom. So because of that, I need to flip the box around to different sides. And now if I want to get a fair measure of how many magnetic field lines are coming in or out of the top surface of the box, what I need to do is scan back and forth across the top of the box and give every point on the box, every square centimeter up there, an equal chance of contributing, and then average all those readings together. So I have this piece of graph paper, which is a 17 centimeter by 17 centimeter grid of graph paper squares. I'm going to put it on top of there. And now I'm going to scan back and forth in sync with the ticking of a clock so that I'll know that I'm giving an equal sampling to every square centimeter. I've got an analog clock here with a red second hand, and I think I remember how to read one of these things. The only thing is that the ticking is not very loud. But wait, it's the 21st century, problem solved. YouTube has lots of videos with sound effects, including the ticking clock sound, which you can now hear, so we can have a nice tick. Because it's a 17 centimeter by 17 centimeter grid, I'm going to take data for 17 seconds. So to help me do that, I'm going to fiddle around in the user interface of this software, which you probably can't see very well. But under experiment, data collection, I'm going to tell it I want 17 seconds worth of data. And the software is now going to graph my data as I go along. You can see that the graph kind of cycles up and down. Each of those cycles is one row coming down the graph paper. And then because the magnetic field is different up here than down here, it's not exactly the same time with each the same pattern with each scan. That little W or cowboy hat shape changes gradually. Actually down near this end of the box there were more positive fields, whereas at this top end of the box, which I scanned first, it was almost all big negative fields. there's no way you'd be able to see it on the video in the computer software's user interface, but there's a way that you can coax it in to give you an average value of the run we just did. So I got that average value. I'm going to go B with a bar on top. That bar on top is sort of a standard way of indicating the average of something. And that was that many millitesla. Then you could just say that average is a pretty good measure of the overall field strength through the top, which is kind of a measure of how many field lines were coming out as opposed to how many were coming in. And you could say, we're done. And that would be fine, actually, for our purposes. And then we do the other 5 sides of the box, add them all up. Actually, there's a more standard way of defining the magnetic flux, which is sort of a measure of how many magnetic field lines pass through a surface. And in that definition, what we do is we take every little area and multiply it by the field perpendicular to that area. And then the next area and the field perpendicular to that, and so on. So when I hold the sensor like this, I am only measuring the component of the field parallel to the sensor, and therefore that is correct for this definition of the magnetic flux, because that's perpendicular to the surface of the box. But I'm not multiplying by the area like I really should to get the real measure of magnetic flux in real units. So if I want to write that definition of the flux in symbols, uppercase Greek letter phi with a subscript b to say that it's the flux of the magnetic field as opposed to something else like the gravitational or electric field. It's defined like this. Here I'm using the sigma notation, which I think you've seen in calculus. So you add up all the little field measurements on each little square and then multiply by the area on each little square. And here we're only taking the component perpendicular to that square. Well, the areas of all our squares are all 1 centimeter, right? So I can take that out in front. And I'll just write A1, because A1 is the same as A2 and so on. And this would just be the sum of all of the data samples that we got. What we actually know is not the sum, we know the average, but you think about in grade school how they taught you to find an average. You add up all the things you have, and then divide by how many things you have, and that gives you the average. So we're going to work backwards. We're just going to multiply by the number of things we have. Multiplying the average by how many things we have gives us the sum of all the things. Then we can kind of regroup these 3 factors. If I take these 2 factors together, this is 1 square centimeter, and when I multiply by the number of square centimeters, I get the total area of the box. So to find the flux in real units through the top of the box, I would take the total area at the top of the box, which is 17 centimeters, multiplied by 17 centimeters, and then multiply it by this value, and to get the SI units, we would need to convert that into Tesla rather than millitesla. I had to stop and do the math, but then the final result is this. It has units of Tesla meters squared because it's a magnetic field multiplied by an area. And the minus sign tells us that there are more magnetic field lines coming into the top of the box than there are coming. So I've done the flux through this side. I'm going to put a little piece of masking tape on there, mark it with a 1 so I can keep track and remember which sides I've done. And now, I'm not going to bore you by showing them all, but the idea is I just rotate it around so a different side is showing, and then I go through exactly the same process again. Here's the graph for side 2. You can see it's a somewhat different shape. It's got big negative spikes. The value is therefore on the average going to be big and negative, and in fact it's about minus 0.05 millitesla on the average, so it's about twice as big and still negative compared to side 1. Here's what I got for my final results. I ended up redoing each side twice and taking the average, and I also did a run in the air with no box there to make sure that I really zeroed things out. Subtracted that background out. With that all done. These are my final numbers. When I add these up, I get this number. And since the uncertainty in each of these measurements is about 0.2, I'm guessing, of these units, if you multiply that by the square root of 6, you get an estimate of the total error. So 0.7 plus or minus 0.5 is really pretty close to 0. It's, what is that, about 1.5 standard deviations away from 0, which does not show that we can disprove our hypothesis. So it looks like the hypothesis that the magnetic field only loops around on itself is correct based on these data. In that experiment, we never found anything that looked like magnetic fields all coming out from a point. And that kind of experiment is kind of mysterious. The reason it's mysterious is because we have electric fields in our universe and magnetic fields, and they behave in almost exactly the same way. In fact, as you get farther into this course, you'll see that the equations about electric fields and magnetic fields are almost exactly the same equations. So why should it be then that we can have this but not this? This is what I would call an electric monopole, or just in more normal terms, an electric charge. So it's a point where electric fields are coming out of it. I'm drawing electric fields in blue because that's what color electric fields are for me. And these things are all over the place. You're made out of them. This is a proton. If the field lines were coming in, it'd be an electron. On the other hand, you draw the same picture, red for me is magnetic fields. This does not seem to exist in our universe. We do experiments like the one we just did, and we never seem to find these. And so why? If electricity and magnetism are so closely analogous, why do we have this kind of thing in our universe, and it never seems like we can find this kind of thing? In fact, a lot of theorists really want magnetic monopoles to exist. They have trouble making workable models of the early universe that result in the right kind of matter coming out of the Big Bang unless you allow them to have some magnetic monopoles flying around. And so if you ask these theorists, they'll say, oh, the magnetic monopoles, they're probably out there. Experimentalists should just look harder. They'll find them if they keep on trying. Actually, when the astronauts brought back moon rocks from the Apollo missions, they actually checked those to see if they had magnetic monopoles in physics labs. And if you had a rock with a magnetic monopole in it, you could do an experiment very much like the one that we just did, waving the wand across the rock. However, a more realistic scenario is probably that these things would be exotic subatomic particles that were created in the Big Bang and have just been flying through outer space ever since then. So they'd be a type of cosmic ray. And then if you want to see these things, they'd be moving very fast. They wouldn't be sitting on your desk. And when they hit the Earth's atmosphere, they would actually stop in the atmosphere. The Earth's atmosphere protects us from cosmic rays and other types of radiation from outer space, which is one of the reasons why we can live on this planet. So if you want to detect these things, a sensible thing to do is send up a balloon up very high in elevation above almost all of the Earth's atmosphere and look for cosmic rays coming from outer space that have these special properties. And then you have to have a different type of detector that can detect what's going on as the particle goes flying through it really fast. So here's a physics paper from 1975 by Buford Price at UC Berkeley, where his team claimed that they saw exactly that. They sent up a balloon experiment, and they claimed that they saw one magnetic monopole from outer space in this experiment. Here's their diagram of their detector, which was just a whole bunch of blocks of Lexan plastic. So it's sort of like old-fashioned photographic film before digital cameras. This particle just comes through these sheets of plastic, and then you just develop it sort of like a photograph, and you get a track. That's that diagonal track going through the detector. And this one they figured out was going at about half the speed of light. And they also found that it was interacting more strongly with the plastic than any reasonable type of matter could have interacted. If they try to analyze this thing as if it were an atomic nucleus, because a lot of cosmic rays are atomic nuclei, the problem is it would have to have a heavier charge than any known element. So they said, okay, this has got to be a magnetic monopole, and it's actually its magnetic fields that are interacting so strongly with the plastic rather than the electric fields of a highly charged atomic nucleus. Well, unfortunately, other people figured out a different way of analyzing this rare event that didn't involve a magnetic monopole. Also, if the Price group had been right, then there would be enough magnetic monopoles that later experiments would have detected a ton of them more easily, because the later experiments were more sensitive. That didn't happen, so it looks like this really was not a magnetic monopole. Nevertheless, there's nothing that says that we can't detect these in the future. People were trying at the Large Hadron Collider, so it's still an open question in physics whether magnetic monopoles exist. So thank you for listening, and if you ever find a magnetic monopole, please let me know.